Hi class, Assalamualaikum and selamat sejahtera. Okay, so today we will talk about the new chapter. It's the early universe. Okay, next slide. Okay, so we will learn about the back to the Big Bang, evolution of the universe, formation of nuclei and atoms, the inflationary universe, formation of structure, cosmic structure, and also cosmological parameters. Okay, for the introduction, okay, as we move backward towards the Big Bang, okay, so the landmarks take away one by one is the first atom vanish, then nuclei, and then even the elementary particles themselves. Okay, so the early universe consists of the pure energy, okay, and temperature, and then expanded and cooled, giving rise to the particles that make up everything we see around us today. So, on the larger scale, the universe is roughly homogeneous, means similar, okay, about the protons, neutron, electron, and dark matter, okay, and the mixture of matter with the radiation and the dark energy. So what is the dark energy? We have learned before is the mysterious repulsive force that permits even the apparent vacuum. And we leave the geometrical flat universe in which the total energy density of all constituents of the cosmos exactly equal to the critical value. So our universe is destined to expand forever. So the cosmic composition based on the observational data, 70% of the total mass of the universe exists in the form of dark energy, with the remaining 30% accounted by matter. So the dark energy currently dominates the density of the universe. Okay, so you can see here the Hubble constant today. Okay, the constant for critical density, dark energy, and matter density. So the cosmic microwave background here is mass radiation that found in the universe. So sorry. Okay, so although this CMU radiation is very weak, it still contains 10 times more energy than being emitted by all the stars and galaxies. Okay, so we have this conversion from the energy to the mass, E equals to mc squared. So the energy in the CMB in terms of the number of photons, space give us the density of the radiation. So it's far lesser than the density of matter and the dark energy. Okay, so in the theoretical models of the universe are constructed by taking into account the effect of Einstein general relativity and also properties of matter and radiation, and assume properties of dark energy. So these models describe how cosmic quantities, for example, density of the components, and change as the universe evolves or around, it means circle around and make prediction which could be compared directly with the observation. So both density matter and radiation will decrease with the expansion, diluting the number of atoms and photons. Okay, so the radiation in the universe is of course will be related to the cosmological redshift. Okay, as you can see this figure, is density that falls faster than that of the matter here. You can see the blue curve and the red curve here. The blue curve is represent the radiation density and the matter density for the red curve. And the constant here, we can see the dark energy density, the green line here. So from a year 0 to 50,000, from the Big Bang, the universe was radiation dominated. Okay, this is how the emission radiation in the ultraviolet. Okay, the dark energy that dominates until now. And also introducing here the Hubble parameter that H in terms of T, that respect to T. Okay, so the particle production, the existence of the CMB implies that the early universe was dominated intense radiation field whose temperature fell steadily as the cosmos expanded. Okay, so the matter was created through a process of pair production, okay, in which two photons give rise to the particle-antiparticle pair, which is the electrons and the positron here. So how about the reverse process? Is a particle and antiparticle can annihilate each other to produce the radiation. So this will lies due to the law of conservation of the mass and also energy. Okay, so it can be concluded that the higher the temperature of the radiation field, so the greater the energy and also the masses. Okay, so we have the threshold for the temperature. Okay, the threshold temperature for electron here and also the proton. Okay, so as that electrons and positron were constantly created from radiation to form the photons again at the same rate, so they are said to have been the thermal equilibrium. Okay, so this is about the universe expansion. So the temperature falls below 10⁹ Kelvin and photons no longer have enough energy for pair production. And only radiation remains. Okay, so we have the process here called the baryogenesis. Is the process of the collision between particles and antiparticles. Okay, so as the temperature drops, matter has frozen out. Okay, and the number of particles has remained constant ever since. Okay, the first 100 seconds of the universe existence. Okay, we know today is proton and electron, and the electron throws out at this temperature. Okay, so the matter creation phase is the evolution ended with the electron. From then on, matter has continued to evolve around and clumping into the complex structure. Okay, so for the first few thousand years after the Big Bang, the universe was small and dense. Okay, so this period is the radiation era, and some matter existed during this time. Is the blending of the gamma ray light of the Big Bang called the primeval fireball. And later in the matter era, then we have came to dominate the atoms, molecules, galaxies, and form as the universe. And today we live in the dark energy era, okay, in which the dark energy is becoming the increasingly important component of the cosmos. So it has 8 significant epochs in the development of the universe. Okay, so here we can see the era that we are talking just now, the radiation era, matter, and the dark energy era. So you can see in details what consists content in that specific era. So before the Big Bang, okay, we come back to the singularity that we have learned before in space curvature in the space-time. So when the universe had zero size, infinite temperature, density, so it will extremely conditioned, so it's breakdown. So at present, no theory exists to let us penetrate the singularity at the start of the universe and therefore describe what came before. Okay, until the theory of quantum gravity have been established. So more of fundamental forces, okay, has some the subparticles that call the quarks. Okay, it's called derived by this novelist here. Okay, so there are 6 distinct type of quark: up, down, charms, range, top, and bottom. And the strong nuclear force, okay, between the atom is a manifestation of the interaction that bind quarks to one another. Okay, I think you can read this one. It's the history of back to the 1960s. And this is leptons. Is 4 feature here. And introducing the new term that combine the strong and electroweak forces is GUT. Okay. Okay, so for the weak forces, okay, is the splitting into the electromagnetic and weak forces. So the key prediction of this electroweak theory were experimentally verified by this guy, okay, and Abdul Salam, okay, that won the Nobel Prize in Physics. Okay, so we have this supersymmetry, SUSY, a notion which extends the idea of symmetry between fundamental forces to place all particles and force transmitted. Okay, so this is about the supersymmetry prediction and particles. Okay, so supersymmetry particles are dark matter candidates, if exist, will have been produced and in abundance in the Big Bang and should still be around today and expected to be very, very massive. Okay, this is the, I think you can differentiate the quarks, lepton, and force particles with this another one. Okay, so now is the theory of everything, TOE, is the idea to combine the gravitation with duties. Okay, so this is the another approach or theory that can support the hypothesis about the introduction of the graviton. Okay, and then we reach into the string theory after that. Okay, about the forces, particles and forces in terms of particle modes of vibration. Okay, we call as the string. A complete theory of the quantum gravity that remain open problem in physics research. Okay, so this is the classification of these 4 forces. And then the period from the beginning of the epoch called named after the Max Planck. Okay, this is the Planck time formula for the quantum gravity. Okay, where the GUT, okay, this one is the GUT, the one that the new approach, the grand unified theory. Okay, so it's predict the 3 forces with were in reality aspect of a single all-encompassing superforce at this temperature. So the quantum physics proposed this idea that forces between the elementary particles, so elementary particles to means the single particles. We have here particle 1 and particle 2. We call it as elementary. So it's exchange of another type of particles that generally called a boson. Okay. Okay, so this is the example how it works in electromagnetism. So the boson involved is the photon, okay? Electromagnetic energy that travel at the speed of light. So the strong force is mediated by a particle known as the gluon G, and gravity theoretical mediated by the graviton. Okay. So we have also the exotic elementary particles. Okay, they should interact only very weakly with normal matter, making them prime candidates for dark energy. Okay, these all the detailed points about the electroweak force, the quarks and leptons that has introduced in the previous figure just now. Okay, so you can read this the characteristic just for your information. The characteristics of each proton, neutron, lepton, and also the previous is the leptons. Okay, so you can read this on your own, I think. Yeah, and neutrinos and also the process that involved here. Okay, this is all the additional point. Okay, maybe you can just read it. Okay. Okay, until we go to the formation of nuclei and atoms, okay, how the formation is begin. So it's begin with the theory of the stellar nucleosynthesis. Okay. Okay, so there are discrepancy between the theory and observation for light elements. So the accepted explanation is that this level of helium is primordial, created during the early epoch before any star had formed. So the production of these heavier elements than hydrogen by nuclear fusion shortly after the Big Bang is called the primordial nucleosynthesis. Okay, so this is the ratio. Okay, this one also the proton-proton chain, and this one proton and neutron chain. I think we also I have included in the final test also, I think. Okay, and also your test 2 pun ada juga kan. So quite a famous question. Because you have to understand how the chain works. So here is the reaction occurred frequently during the lepton epoch. However, they were broken apart by gamma rays as they form. Okay, so the waiting period is known. The deuterium bottleneck was needed until it became full enough for deuterium to survive. Okay, so this is the helium formation in the early universe. Okay, this one is the reaction. Okay, maybe you can just take a look. The reaction, how the reaction here, and the in the form of a graphic. Okay, you can simply compare here where is the production of this into helium-3, okay, and energy here. So you can see this reaction one by one from this figure. Okay. And of course, it's related to the main sequence star for the helium formation in the universe. And then we have amount of lithium also with the reaction. So this is the total mass of matter 1/4 with 35% accounted by the helium and 75% from hydrogen. Okay, I think I stop here in the slide of 42. Okay, for the helium formation. Okay, we finished for the helium formation. So we continue in the next lecture. Okay, thank you.